Hello everyone, today I will be presenting a paper called Inner Monologue, Embodied Reasoning Through Planning with Language Models. This work was published at CORL 2022 by a large team at robotics at Google. Let me walk through the key ideas and results. Here's the roadmap for today. We will start with the motivation and the problem the authors are trying to solve. Then I will explain the inner monologue method itself, covering how it works and different types of feedback it uses. After that, we move into the experimental results across three distinct robotic domains. We will then look at some surprising emerging capabilities the system exhibits. Finally, I will cover the limitation and wrap up with a conclusion. The core challenge the paper addresses is that intelligent robots need to do three things simultaneously. First, they must draw on a large repertoire of basic skills. Second, they must chain these skills together over long time horizons to complete complex tasks. Third, and most importantly, they must recognize when something in their plan is going wrong and adapt in real time. This is hard. Conventional approaches like task and motion planning or hierarchical reinforcement learning address parts of it, but they struggle with the semantic understanding needed for open-ended real-world instructions. The authors draw inspiration from how humans think. When you are trying to unlock a door, you have an inner monologue running. You try the key, it does not fit. You try another one, that one works. Now you turn it. The process naturally combines goal-directed planning, observation of outcomes, and corrective action. The key insight in this paper is that large language models can play the role of this inner voice, but only if they are given closed-loop feedback from the environment. Without that feedback, the LLM just generates a plan once and has no way to know whether the robot is succeeding or failing. To understand these contribution of the contribution of this paper, it helps to know what came before. Second, a prior work from the same Google group showed that you can ground LLM plans using the affordance functions of low-level control policies, so the robot only attempts actions it is physically capable of performing. So Socratic models show that language can serve as a shared interface between different pre-trained vision and language models. Both of these are important steps forward. However, all of these prior systems share a critical limitation. The LLM is used in a one-directional way. It produces a list of skills at the beginning, and the robot executes them. There is no channel for the environment to report back to the LLM. The LLM cannot know that a grass fell, that an object moved, or that the human changed their mind. That is the gap this paper tried to fill. The authors ask, if we given the LLM natural language description of what is happening in the environment at every step, how much does planning performance improves, and what new behaviors emerge? Crucially, they want to do this without any additional training, using only few-shot prompting. Let me formalize the setup. The system receives a high-level natural language instruction from a user, for example, bringing a soda from the fridge. The robot has access to a library of pre-trained short horizon skills, each described by a short text label, such as open the fridge door or pick up the soda can. A pre-trained LLM acts as the planner. Given the instruction and a few in-context examples, it selects which skills to execute in sequence. None of this is new. What inner monologue adds is the observation variable O, textual feedback from the environment, which gets injected into the LLM prompt after every skill execution. There are three categories of feedback the paper studies. Success detection tells the planner whether the last skill succeeded or failed. Passive scene description continuously tells the planner what objects are visible and what has changed in the scene. Active scene description allows the LLM planner to ask questions directly, which are then answered either by a vision question answering model or by a human. The right-hand figure shows examples of each type in the actual prompt format used. The formulation is conceptually straightforward. At every planning step, the system takes the current state of the LLM prompt, which already contains the task instruction and the history of executed skills, and appends the latest environment feedback before asking the LLM to predict the next skill. This creates a running dialogue between the robot and the environment, hence the name inner monologue. Success detection is binary. In simulation, the authors use scripted oracles that have access to ground truth state. On real robots, they train a visual classifier to detect success. Passive scene description includes object recognition from models like MDETR, which outputs a list of currently visible objects. In the simulated domain, they also include a task progress description that tracks which sub-goals have been achieved so far. Active scene description is the most flexible type. The LLM generates a natural language question and the human or VQA model answers it. This lets the system handle ambiguous instructions or unexpected situations by asking for clarification. Three key properties make this practical. No fine-tuning is needed. The same formulation works with different LLMs such as InstructGPT and PLM. And in principle, any feedback that can be expressed in language can be plugged in. The figures on the slide shows how inner monologue is instantiated across the three experimental domains. All three share the same general structure. A human given a higher level instruction, the LLM decomposes it into actionable steps, and embodied feedback from perception models is injected back into the prompt. But the specific feedback models and the low-level control policies differ across domains. The top row shows the simulated tabletop environment using Ravens and InstructGPT. The middle shows a real UR5E arm with MDETR for object recognition. The bottom row shows the everyday robot mobile manipulators in the real kitchen, building on the Seiken framework with PLM as a language model. This diversity is intentional. The authors want to show that the inner monologue formulation is not tied to any single system. The first experiment used a Ravens-based simulation environment where a robot arm must rearrange blocks and bows according to natural language instructions. There are 4 scene tasks used for few-shot prompting and 4 unseen tasks used for zero-shot evaluation. Gaussian noise is added to pixel observation, policy output, and place locations to simulate realistic disturbances. The baseline is clipboard, a strong single-step manipulation policy that is directly trained on long horizon instructions. Looking at the result table, a few things stand out. First, clipboard gets 0% on every unseen task because it has no mechanism for generalization to new task descriptions. The LLM-only variant with just object feedback already jumped to 20 to 62% on unseen tasks simply by leveraging the semantic knowledge inside the pre-trained language model. Adding success detection on top of object feedback improves performance further by enabling the planner to retry failed actions. The best variant, which adds task progress scene description, achieves the highest scores across the board. On the challenging unseen matching bowls task, it reaches 82%. The takeaway is clear. Richer feedback leads to better planning, and the LLM generalized to unseen tasks without any retraining. The second experiment moves to a real robot, the UR5E arm with a wrist-mounted RGBD camera looking at the tabletop, covered with a toy blocks, food items, and condiment. Object recognition is handled by NDETR, a pre-trained open vocabulary detection model. Pick and place is executed by zero-shot primitives that use the LLM to parse target objects from language command and then move to the center of detected bounding boxes. No task-specific training is done. To stress test recovery, the authors inject 4 millimeters of Gaussian noise into every action. Two tasks are evaluated over 10 rounds each. The first is completing a 3-block stack where 2 blocks are already pre-stacked. The second is sorting food items onto one plate and condiment onto another, where the LLM must autonomously decide which category each object belongs to. The results are striking. Using only the open-loop object description from the start of the task achieved just 20% overall. Adding either object or success feedback individually gets to 40 to 45%. Combining both feedback jumps to 90% overall, including a perfect 100% on the stacking task. The ablation tells us why. Object feedback catches objects that were occluded at the start and missed by the initial scene description, while success detection catches action values that need to be retried. The third and most complex experiment uses the everyday robots mobile manipulators in a real office kitchen. Built directly on top of SACAN framework, PALM serves as the language model's SACAN affordance function still provides grounding for which actions are physically feasible, but now in the monologue adds closed-loop feedback on top. A learned visual success detector, a human-provided object recognition. 120 evaluations are spread across 3 task families: general manipulation, dexterous drawer task, and long horizon mobile manipulation that combines navigations and manipulations. Results are reported both without disturbances and with adversarial disturbances, where a human physically interferes with the robot to force policy values. Without disturbances, adding inner monologue feedback already improves SACAN by 5 to 25% points, depending on the task family, but the disturbance setting is where the results become dramatic. SACAN drops to essentially 0 on mobile manipulation because it has no way to recover from a forced failure. Inner monologue with object and success feedback achieve 75% on the same task. The total improvement is from 31% for SACAN to 60% for the full inner monologue system. This demonstrates that closed-loop feedback is not just nice to have, it is essentially for robots' real-world deployment. Beyond the quantitative improvement, the paper documents several surprising emergent behavior that arise from the inner monologue formulation, none of which were explicitly included in the few short prompt examples. The first is continued adaptation to new instructions. In the kitchen experiment, a human changes the robot's goal mid task and then later says, finish the previous task. The LLM correctly checks both goal changes and returns to the original task. In a separate instance, when told, please stop, the LLM correctly predicts a dumb action, and even though this pattern was never shown in the prompt examples. The second emergent behavior is self-proposing goals under invisibility. In the simulated tabletop domain, the task is to put two blocks in a purple bowl. The system tries to pick up the purple block, which is intentionally made too heavy. After receiving the hint, the purple block is too heavy, it autonomously proposes to find a lighter block and successfully complete the task. This is remarkably human-like problem solving and was never explicitly prompted. A third emergent capability is multilingual interaction. When the human provides a new instruction in Chinese, the LLM correctly interprets it, re-narrate the goal in English and the prompt for the prompt history and replans accordingly. The authors know this even extends to symbols and emoji in some cases. This falls out for free because the underlying pre-trained LLM already has multilingual understanding. The fourth capability is interactive scene understanding. After completing a task, the authors ask the system questions about the current state of the scene, questions that require reasoning about the history, actions, and feedback. The system can often answer these correctly because the full inner monologue is still in the prompt context. The appendix also documents two additional robustness properties. The system handles feedback injected in an unexpected order, and it correctly interprets instructions with typos, both inherited directly from the robustness of the underlying language models. The authors are transparent about several important limitations. On the assumption side, the main experiments rely on Oracle sim descriptors, either scripted system in simulation or human observers in the real world. The appendix does include a result with fully learned replacement using MTETR and the visual success classifier, which perform reasonably well, but the gap to Oracle performance is real. Unvalued models are false negatives from the success detector cause the robot to unnecessarily retry actions that already succeeded, wasting time and potentially disrupting the sim. False positive, conversely, makes the robot think a failed action succeeded and move on, which compounds errors. In some cases, the LLM simply ignores the feedback and continues planning with objects that are no longer present. The deeper structural limitation is that the quality of low-level control policies act as hard ceiling on which the high-level planner can accomplish. No amount of clever replanning can compensate if the robot cannot reliably grasp objects. Further work includes building fully automated pipelines with modern image and video captioning models, or developing better methods for aggregating uncertain or conflicting feedback sources, and incorporating safety and ethics constraints directly into the feedback loop. To summarize, The paper makes one central contribution. It shows that given a large language model close to natural language feedback from the environment dramatically improves long horizon robot planning. It, it does so without any additional training. The inner monologue framework is general. It works with different LLMs, different robot platforms, different environments, and different feedback sources across three domains: simulated tabletop, real tabletop, and the real kitchen mobile manipulation. Adding feedback consistently and substantially improves task success rate. The gains are especially large under adversarial disturbances, where a baseline system that lack retry and replanning mechanism essentially fail completely. And as a bonus, the framework unlocks emerging capabilities like multilingual interaction, goal self-proposal, and interactive sim understanding. I think a broader takeaway for this field is that language is an exceptionally powerful interface, not just for giving robots instructions, but giving robots a sense of what is happening around them. The inner monologue metaphor captures something genuinely important about how intelligent behavior works. That's it. Thank you, and I'm happy to take any question. Please leave a comment if you have any. Thank you.